All right, ladies and gentlemen, so let's review real quick what we discussed in class. Now, today's class was a relatively short class, and I'm going to review a little bit of the theory that was discussed and actually talk about doing the electron configuration, the noble gas notation, and the orbital notation. Now, I slightly varied from the example that's in the book because I made it more relevant to the homework assignment that you guys have assigned. So I've slightly changed it, and we're going to see it in this video. So we're going to talk about what we did in class today was reviewed a little bit about elements of the fourth period. And we talked about some of the exceptions of the elements to Hund's rule. Um, and we said that elements of the fourth period elements are elements that begin to fill, and it says the 6s. Obviously, that is a mistake. Let's see if I can correct that real quick. It's not elements of the elements begin to fill the 6s orbital. That is incorrect. It's elements that begin to fill in the 4s orbitals. So let me go ahead and correct that for you guys. So it's our fourth period elements are elements that begin to fill the 4s orbital. Now, of course, they follow the 4s orbitals, the 3D, 4p, and all that order that we already talked about in class. And there are some elements, or fourth period elements are elements basically that start from scandium all the way up to zinc. And there are some elements in the fourth period that actually don't follow Hund's rule as expected. And the reality is that there's no simple explanation for that other than they basically don't follow the expected order because it's the most stable configuration for them. And remember that elements try to maintain the most stable electron configuration possible, which is why they try to have a complete octet. And then after that, we talked about elements of the fifth period. And elements of the fifth period start to fill the 5s orbitals. After this orbitals, the 4d orbitals is filled and followed by the 5p orbitals. And the elements that are elements of the fifth period are basically rubidium all the way up to xenon. And just like in elements of the fourth period, they also have elements that don't necessarily follow Hund's rule in order to establish stability. And then after that, what we did was we talked a little bit about electron configuration, complete electron configuration, noble gas notation, and the orbital. Not the orbital notation. There were actually some other questions, but because of the homework assignment, I decided to just talk about the electron configuration, the orbital notation, and the noble gas notation. So let's go ahead and let's talk about iron. And iron has an atomic symbol of Fe, and the atomic mass of iron is 26. And what that means is that there are 26 protons, and the number of protons equals the number of electrons. So there are also 26 electrons, which means that I can configure the or make the the electron configuration. Now, what I'd like to do is actually start with the orbital notation first, and then we'll work our way up to the electron configuration. So if we do the orbital notation, we know that all elements start at 1s, so that would be 2 electrons here pairing this orbital. And then after they fill up the 1s, they'll go to the 2s, which also has one sublevel, and it fills up the orbital with 2 electrons of opposite spin. So that'd be 1 right here, and then the other electron. After that, we know that they go to the 2p orbital, and remember that the 2p orbital does have 3 sublevels, so they fill up the entire 2p orbital, and that would be 6 electrons. So this is the orbital notation, what we're doing here. And this is so you guys have an idea of what you need to do for the homework assignment, right? The orbital notation. And After that, we go to the 3s. And of course, the 3s also fills that orbital with 2 electrons of opposite spin. So you're going to have 2. And then the 3p orbital. Now, in orbital notation, remember that we are drawing our lines which represent the sublevels, and we have to follow the order according to Hund's rule. So 3p also has 6. Now, if you're getting a little confused, sometimes what I do is, as I'm doing the orbital notation, I'll go ahead and I'll count the arrows, right? Of course, the arrows that represent the electrons, and I know I have 2, 4, 6, 8, 10, 12, 14, 16, 18, and I need 26. So that means I still have 8 more to go. Now, we don't go from 3s to 4 to 3d. We actually go up to 4s. Remember that we pair the electrons from the lowest sublevel possible, so 4s. And according to that, we fill up the 4s, and it has 2 more. So again, I count. I go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I still need 6. Now I go to the 3D. I go to the 3D sublevel. And I go to the 3D sublevel, and the 3D has 5, or 3D orbital, excuse me, and it has 5 sublevels. It has 5 lines. So I need to fill up the remaining electrons. And to fill up the remaining electrons, well, I know that I need to arrange them. So, and I'm missing one more. So we'll start, always remember, we start filling the first, right? And we have 1, and then we have the other electron with opposite other, filling the other sublevel here. Sorry guys. So we fill up 1, and good time to kind of start counting to make sure that I do have my 26 electrons paired. So I know I have 1, 2, 3, 4, 5, and I have 5 here, and 2 here, 7, 9, 11, 13, 15, 17, 19, 21, 23, 25. So I'm missing 1 more to have the 26. So then I would just add the other electrons, add the other arrow with the opposite spin, meaning that now I have 26 electrons, which is the atomic number, which is equal to the number of protons, which is equal to the number of electrons. So this is my orbital notation. Now, the other thing that the problem wants us to do is to find the complete electron configuration. So when we're doing the orbital notation, very important to understand that from 3p, I go to the 4s, and then I go back to the 3d. Now, when I'm writing the electron configuration, I don't do that. I actually, follow the number according to Hund's rule, or the following the quantum number. So 1s2, because I have 2 electrons, that would be the electron configuration. I have 2s2 here because I filled that up. Then I go to 2p6. Then I go to 3s2. Then I go to 3p6. Then I go to 4s2. Then I'll go to 3d. I'm sorry. When I'm doing the electron configuration, excuse me, I almost made the mistake that I told you not to make. When you're doing the electron configuration, instead of going 4s2, which is what we did in orbital notation, we write the 3d, because even though I go to the 4s because it has one sub level, and then I fill up, I go to the lowest possible sub level. The quantum number is 4, and 4 is larger than 3. So to follow Hund's rule for the electron configuration, we actually say 3p6, 3d6 as well, and then we go and write 4s2. Okay, so it's very important to not confuse the orbital notation with the electron configuration. The orbital notation, ladies and gentlemen, the orbital notation has the arrows, and the electron configuration um, and the electron configuration uh, does not follow that order. So in the electron configuration, I do write the 3D and then the 4s. And then finally, to write the noble gas notation, and you can look for this at the periodic table. If you look for iron at the bottom of the periodic table where the atomic symbol of iron is at, it has the noble gas notation. And it is argon, which is the closest element that fills that octet. Okay, argon, it's a noble gas that has this closest possible octet to complete the octet rule. And then argon, and then of course, well, since it is a notation, we write 3d6 because it's 3 is a lower quantum number than 4. And then finally 4s2. So ladies and gentlemen, hopefully this video will help you guys work on that homework assignment. So stay safe, and we'll see each other in our next class. Bye-bye.